Welcome to my Introduction to Networking course, also known as ITN. This is the version 7 material preparing learners for the Cisco CCNA 200-301. Cisco curriculum, everything is owned and copyrighted by them. Module 4, the physical layer. So in the physical layer, we're talking about the purpose, the characteristics, and we're looking at the three main types of physical cabling: copper, fiber optic, and wireless. Yes, I understand wireless is not tangible, but it is classified as one of the physical layers, so we're going to talk about it in this module. So what's the purpose of the physical layer? Essentially, before any communication can occur, there has to be that physical connection between multiple devices. That has to be established. Again, wireless is also included in this. This connection could be, again, wired or wireless. And how we do that is through an interface card, oftentimes called a network interface card, or NIC. The NIC, if it's wired, will be a wired NIC. If it's wireless, it will be a wireless NIC. If it's cellular, it will be a cellular NIC, and so forth. These interface cards allow us to gain connection to whatever type of network we're trying to connect. Some devices may only have just one NIC with one port. Some devices may have multiple NICs, both wired, wireless, and other. Some devices, like a mobile phone or a cell phone, may have a cell phone, a cellular NIC, a wireless NIC, and a Bluetooth NIC. They may have more than just two. They may have multiple. Again, not all physical connections offer the same level of performance. Wired versus wireless, which is going to be better? That's outside the scope of this lecture, but that's one of the big topics that will be discussed when you're in the networking realm. What is going to be a better option? So what's interesting is the physical layer actually takes the frame, Ethernet frame, takes the packet and the segment and the user data, and actually takes that entire package and it puts it into bits. The bits are electrical signals, typically, that go on the wire. If we're talking fiber optic, it may be light pulses. But essentially, we're looking at taking the packages and making it go on whatever physical media we are selecting. This is the last step in the encapsulation process. Again, we take the entire package, we break it down into manageable chunks, and we send it on the wire. And this allows us to go from our device to the next device in the network. If it is local traffic, it's going to go to that, probably a switch. If it is internet-based traffic, it will be packaged to be sent to the switch, from the switch to a router, and from the router to the internet. Essentially, each device will receive the bits, and then it will take it and it will reconstitute a frame out of those bits and decide what to do with it. So, what are some of the characteristics? Well, first of all, we're talking layer 1, so that means we have to look at the different standards, things like IEEE standard, the IATIA standard, the ITU standard, the ISO standards, and so forth. These are governing bodies that outline how physical media should be. If we're talking copper cable like UTP, an Ethernet cable, well, how do we know how the cable is made? How do we know about the connection that is made? Well, those are all IATIA-based standards. If we're talking how the signal is put on the wire, IEEE lays out the standards for how the electrical signal is put on the copper-based wire. So these organizations actually outline how these connections should operate, how they should be made, how they should be terminated and tested. So major components of the physical layer addresses different functional areas. That's going to be the physical component, the cable itself, the signaling, and the encoding/decoding of that signal. So the physical components, again, are the hardware, the media, the connectors, the connections, anything that is used to transmit the data, and that's going to be wired NICs, wireless NICs, the connection of the cable itself, all of those things. So let's talk about encoding. Earlier we discussed binary. Here is why binary is so important, because our bits are actually all binary bits. So encoding basically takes and converts the stream of bits into a format that's recognized by other devices on the network. Here we have voltage over time. And as we look at the time as it goes on, what is represented as a 0 and what is represented as a 1? That is going to be the encoding. You'll notice that a high rise in the middle of anything represents a 1. In the middle of each option, if it's declining, it represents 0. And again, this is just for example. Here, this is a high rise, though this is falling, so this is a 0. While this is still high, when it gets in the middle, it falls, so it's a 0. Here, it's a high rise, and in the middle, it's rising, it's a 1. Here, same thing. It's a high rise, and in the middle, it's going up, so it's a 1. Here, even though it's high in the middle, it's falling, so it represents a 0, and so forth. There's different methods for encoding. It all depends on what we're trying to process. So when we talk about signaling, we can talk about maybe the digital signal being a positive or negative voltage connection. Maybe we talk about the amplitude, the height of a signal, AM, amplitude modulation. Maybe we could talk about the frequency modulation. That's the frequency, that's the length of the signal over a given period of time. Here we're talking height. Here we're talking length. Here we're talking our phase. You'll notice that here the phase shifts. If we're talking fiber optic, it's going to be light pulses. So again, it just kind of depends on the type of media that we're using to represent those 1s and 0s. So let's talk, how do we measure this? We measure the actual transfer of bits in 2 ways. Bandwidth, and that is the maximum capacity that a medium can carry. Not the actual, but the maximum. And how we actually state bandwidth are in bits per second. Little b PS. Whether it be bits, kilobits, megabits, gigabits, terabits, and so forth. It is different than gigabyte, big B. If we're talking storage, we're talking big B. If we're talking actual communication, we're talking little b. The difference is there are 8 bits in 1 byte. So there's a different factor of 8 when we talk little b versus big B. When we talk specific bandwidth, we have to understand certain terminology. Latency, that's delay. That's typically the amount of time that it takes to send a signal, including that delay. Throughput is the other form of actual measurement of data flowing through a wire. Throughput is the actual measure of bits being transferred. And goodput is the measurement of usable data. So basically goodput is throughput minus the overhead. Overhead are going to be things like the frame headers, the packet headers, resending, if we're having to do acknowledgments. All of that is traffic overhead. That's not part of the data. Throughput is the actual transfer of data. So now that we have some basic understanding of how we measure, how we have basic characteristics of the different medias, let's talk about what those medias are. Again, there are three main types: copper, fiber, and wireless. And that is this chapter in a nutshell. If you have any questions or concerns, please reach out.